Factor the polynomial completely. 12a squared minus 27b squared. What we have here is a polynomial. It's a binomial because it's a two-term polynomial, and we're being asked to factor it. Now the basic meaning, intent of factoring, our basic goal is to take what we're being asked to factor and express it as at least two factors times each other. Take what we're being given, which is really a difference, it's a difference of two terms, subtraction, and we're going to turn it into multiplication. That's kind of the abstract, a little bit abstract for some students, many students. So let's copy down what we have here. We have a 12a squared minus 27b squared. And it's always good practice when we're factoring a polynomial to first look for a greatest common factor. So because several advantages. If we look for a greatest common factor, a GCF, it'll reduce the numbers down, to where we have smaller numbers to deal with moving forward with our factoring of the polynomial. So the first easiest things to include or exclude in our GCF are variables. I see a's are in the first term but not in the second term, and b's are in the second term. There's a b in the second term but not in the first term. A and b, neither one of them should appear in our GCF because they're not common to both terms. Now we can focus on the numbers, and I just do by factor trees. First two numbers I can think of for 12 are 4 and 3. We could use 2 and 6. We could use a variety of factors as long as they're correct. There's no problem. There's no perfect two numbers, and then 3 is a prime number. So inside of 12 we have two 2's and a 3. Inside of 27 we have 3 times 9. 3 is a prime number, gets a vertical line. 9 is composite. It breaks up again. So we have 3 3's. Now across these, a greatest common factor is looking for identical factors in the first term as appear in the second term. So look, we are able to match up a 3. For every match, we report to the GCF one of those. There's a match of 3. There's a common factor of 3. I look for more common factors, but 2's don't appear in the second term factor tree. These are two factor trees, and 3's don't appear. Any unmatched 3's don't appear in the first factor tree. So there's a one factor of 3 that forms the GCF. GCFs can always be positive or negative. So now that we have used some construction underneath our polynomial, let's start with a clean copy. 12a squared minus 27b squared. And we're about to factor out the greatest common factor, so I like to put an empty set of parentheses right underneath our polynomial. It's a binomial. There's a two-term polynomial, and we're going to need to open up two blanks, one for each term, so that when we factor the GCF out, here's the GCF. I write it right underneath there to the outside of this, what I call the remaining polynomial, and we're going to make this, we're going to put in everything we need in these two blanks so that the GCF, when it distributes to the first blank, it makes the first term come back, distributes to the second blank. We have all the parts in here to make this second term come back. So what would we need in here? Well, first of all, we're trying to make a positive 12a squared come back. So which sign should we use of the GCF? The positive 3 or the negative 3? Well, let's figure it out. For something times positive to make positive, we would have to use the positive version of the GCF. Positive times positive is positive. Now let's move on to the numbers. 3 times, what would I need here? A factor of 4. 3 times 4 makes 12. And then we would need all of this a squared in this blank to make a squared come back. So let's check it all. Positive times positive makes positive. 3 times 4 makes 12. A squared. Great. We have everything we need in this blank now. Now let's distribute this 3 to the second blank. And what would we need in here? always start with your sign first is my recommendation. Positive times, we're doing multiply, so I'm following rules of multiply. Positive times negative. We need a negative right here. Positive times negative to make negative. 3 times 9 makes 27. And we need the b squared to be in this blank, because there are no b's that appear in the GCF. Okay, now part of our goal, we do have two things times each other, but we're also tasked to look to see if we can continue factoring the remaining polynomial that's in green here. So I notice that it's a binomial. This is a binomial, and it's a difference binomial. Look, it may fit the pattern of what a difference binomial, a difference of perfect squares binomial could be. So we have to analyze this and see if we can continue factoring. If it does factor, look, the factors of a difference of squares, difference of perfect squares binomial, would factor as a plus b binomial times a minus b binomial. A and b come from the square root of a squared and the square root of b squared. Okay, let's look at our specific green remaining polynomial. In the a squared position, we have 4a squared. In the b squared position, we have a 9b squared. To reveal that, verify that these are actually two perfect squares, which we do. We have to make sure of that before we fill in any parts of our formula. We're going to take the square root of a squared and the square root of 4a squared to determine those things. The square root of a squared is a, the square root of 4 is 2, and the square root of a squared is a, right? So we verified that 4a squared is a perfect square. Now let's take the square root of both sides of this little equation. It'll tell us what b is. Square root of b squared is b. Square root of 9 is 3, and the square root of b squared is b. Yes, it came out clean. So 9b squared is also a perfect square, and there's a minus between them. It fits all of the parts of a difference of squares. Now we may proceed to fill in these parts to further factor our polynomial. It fits the pattern of a perfect difference of perfect squares. So we're going to continue factoring the remaining green polynomial in this way. We're going to fill in the parts of a and b. We're going to replace a and b in the formula with our a of 2a. Our a is 2a. So it goes in both of those spaces delegated to a. And our b in our problem replaces b in the formula. Our b is 3b and 3b here. And don't forget, we need the GCF to also be included as one of the final factors. We were thinking there were going to be 2 factors because that's the minimum goal of factoring. However, we have a GCF times 2 binomials as our factors. Now, we could check these. I encourage you to check them. We would first FOIL the 2 binomials together, then redistribute the 3 across that trinomial that we would, in this case would be a binomial that we would get. And you'll find that it'll take us back to our original binomial. For the sake of time, I'll leave the check step to you. Now let's verify which answer choice of the answer selections would match what we obtained as our correct factors. Okay, we're looking for a factor of 3. Are we able to find a factor of 3 in any of the answers? We find one here in answer A. There's no factor of 3 in answer B. What they've done is they've left a factor of 3 inside one of these binomials, but that's incorrect because we're always supposed to factor completely the way we did. There is a factor of 3 in answer C and a factor of 3 in answer D. So A C and D are possibilities. Now let's look for this other correct factor of 2a plus 3b. We look here, we only find it in answer A, choice A is incorrect factor, and there's we're not seeing what we require. We can eliminate, this is incorrect, we can eliminate A as a possibility. When we come down to C, I'm not seeing 2a plus 3b. I see 2a plus 3b, but squared means that they're implying there's another factor of 2a plus 3b. And that's not true, because our other factor is a 2a minus 3b. So now we eliminate answer choice C, and what do we find? 2a plus 3b appears in answer D, and 2a minus 3b also appears in answer D. So our correct answer choice is definitely answer choice D. It has all of our correct factors in it.